My talk of today will regard actually the same system as you found before, but with something more related to the possibility to have a reversible actuation. And I will do this by first introducing our interest towards reversible shape memory effects in polymers. Then I'll specify the aim of the work. I will focus on how the material were prepared, on the structure and thermal properties, and my results were mainly regard this specific reversible two-way shape memory effect as it could be achieved under stress-driven or stress-free condition. And I'll provide you even some early results on the first system we printed by 3D printed facilities. So I'm coming from the community of shape memory polymers, and as we often say when dealing with the shape memory properties in polymers, more than an intrinsic property is rather a combination of macromolecular architecture and a specific thermomechanical history. The most common effect is the one-way shape memory effect, by which we can deform a material in a temporary shape and make it revert back to the permanent shape by the application of a thermal stimulus or an external stimulus. And this may serve greatly for biomedical applications, smart textile, and of course in 4D printing, or at least in some of the 4D printing strategies. But this cannot be considered a fully reversible effect, since for applications such as, for example, artificial muscle or gripper for soft robotics, the possibility or the ability of the material to undergo elongation and contraction or changes between two specific shapes under application of on-off stimuli, such as cooling and heating, is something more than typically shape memory polymers cannot guarantee. So from the early start of shape memory polymers, there were various attempts at obtaining this reversible effect. The former one were more extrinsical and were relied on combining various materials, also in multi-material printing solution. And other researches were devoted to intrinsically obtaining this effect. And as often in shape memory polymer, this is achieved by combining specific polymers and specific thermomechanical histories. The two most important effects are known as the stress-driven and the stress-free or reversible two-way shape memory effect. The first one could be achieved with semicrystalline network and liquid crystalline elastomers, and it usually occurs by applying a fixed load to the material and subjecting the material to cooling and heating across some specific region. The second one, the stress-free, is quite related to the former one, since in this case, the transition between the two shapes occurs apparently without any stress, an external stress applied, and it relies only on internal stress. And this internal stress is provided by a partial melting of the structure. So for example, in the picture you can see here, it is the stress in a biphasic system that is provided by a certain crystalline phase with respect to the remaining amorphous one. The former being often called as a skeleton phase, the other one being called as actuation. And although this effect is more complex, interestingly, it may be achieved by a larger number of polymers. They may be homopolymers, copolymers, and they may be cross-linked physically or chemically. So we thought about focusing on semicrystalline networks, and this because this family is particularly versatile in providing more than one shape memory effect, and also because they're relatively easily tuned through the cross-link density. And in this work, we'll collect the preparatory studies towards 4D printed system, and in particular, we focus on PCL, PEG copolymer networks, and that were cured by photo-crosslinking, and we studied the effect of the material composition and of the thermomechanical cycle on the two-way shape memory properties. So the system were obtained by first and capping polycaprolactone and polyethylene glycol with methacrylate and terminals, so to be reactive with the UV light. And the structure obtained is provided here in the scheme, and it may be described as a network in which net points bind together a multicrystalline structure with a different kind of crystalline parts. We choose particular molecular weights and specific PCl to PEG ratios in order to have a separate melting and crystallization temperature for the two phases. This was the target of our composition. And as I will show you, we also carried out some experiment on PCl and PEG homopolymers. Here are the three ratios we investigated. As you can see from DSC, the melting and crystallization temperature of the two phases are separate and are the same for all the systems, whereas the amount of crystallinity clearly depends on the specific amount of PCl or PEG. And its effect then can be seen also on the mechanical properties if you see the different increase or drop of the storage modulus throughout the DMA test. And the DMA tests are also important in showing us the good plateau, the very stable rubbery plateau, which suggests that the material is effectively cross-linked. And this effect is also confirmed by swelling experiments. The two-way shear memory effect was investigated by means of a DMA machine on tensile bars cut from the material obtained. And the machine was particularly useful since in order to understand this effect, we have to simultaneously track and control stress, strain, and temperature throughout the specific thermomechanical cycle, as for example is here depicted for the one-way shape memory effect, which allows to evaluate for all the material a good strain fixity, the ability to fix a given temporary deformation in the material, and also very high values of the recovery strain. Here is the typical cycle by which the stress-driven two-way shear memory effect is investigated. The material is first heated above both melting temperature, is subjected to a fixed load, and then is cooled under this constant load. And you can see that during cooling, the material undergoes a significant elongation that takes place in particular close to the crystallization temperature for the two phases. And the effect may be reversed by heating and melting the two phases so that the material in the end attains a levels of strain that is quite similar to that shown before cooling. And the effect may be interpreted as a consequence of a structural evolution. In fact, it is known that when material crystallizes under a given strain, the stress that is required to maintain this shape is reduced. So in this case, where the stress is kept constant, we have a further elongation of the system, and this allows to have this cooling-induced elongation. And of course, when removing these crystalline constraints, the material moves back to the equilibrium condition in the rubbery state. Here the results are reported for the three materials. We can see that more or less the elongation is the same for all of them, and the difference regards mainly the amount related to the PCl and PEG phases. And the reversibility, which is described as recovery magnitude, is very high for all these systems. The graph is also particularly interesting to us since it provides us an important parameter that is called in literature separation temperature, which represents the temperature that stays between the full melting and recovery of the PEG phase and that is pristine the melting process in the polycaprolactone phase. So taking this parameter, we could perform the more articulate cycle for the stress for the stress-free condition, which has the same first step as we showed before. We have heating above TM, application of a strain, and elongation under the fixed load. After this, we have unloading, so the load is fully removed, and we promote a partial melting of only the PEG phase while maintaining the polycaprolactone phase as skeleton phase and as a stress provider throughout the structure. After this, that we can call a training cycle, the material is now able to undergo, without no external load, a cooling, an elongation and contraction cycle upon cooling and heating across the melting temperature of the PEG phase, which is the actuation phase. And this effect is shown to be very stable, thanks to the, as you can see from the repeated experiment. And this is due to the very strong phase provided by polycaprolactone, and may also be applied, for example, under flexural conditions. So we have opening and closure of these bars under exposure to high and low temperature. Here is the effect reported for all the system. It is more or less similar in let's say, the shape of the curves, and we have, as expected, a higher effect in the case of the material richer with PEG, which is actually the actuation phase. However, you can see that the values of the formation are much lower than we found for the same applied pre-stretch in the case of the stress-driven effect, and we compared this for various levels of pre-stretch. You can see, in fact, that while the stress-driven keeps in increasing with the pre-stretch, so it's quite reactive to this as tailoring parameter, the case of the stress-free remains very small and rapidly attains what can be considered as a condition, a steady state for the value of the maximum elongation that may be obtained. This is far by being a limit. In fact, the stress-driven elongation may perhaps work good as in the case of artificial muscles. So we have systems that are capable to be highly controlled in lifting and lowering certain loads. Whereas in the case of the stress-free condition, the smaller levels of load, of strain, may be more compatible with the case of flexural deformation and may be very useful for realization of smart hinges or smart grippers for soft robots. And as you can see, you can fully control by temperature the amount of opening and closure of this hinge or gripper up to levels values of angular variation up to 180 degrees. And however, we try to see if we can further tune the effect and increase the amount of elongation. So we tried first to work on the separation temperature to promote more, let's say, erosion of the crystalline part. And we find out actually that in the case of PCL, the effect becomes quite important. In particular, it reaches values up to about 12%, which is significant with respect to the other found. And we also try to see if by this idea, a strategy related to just an homopolymer could be useful. And these are the results reported in the case of a homopolymer polycaprolactone system in which the same crystalline structure plays both the role as the skeleton phase and as the actuation phase. And as the results suggest, it is possible to greatly increase the stress-free, also the stress-driven, but in particular the stress-free elongation related to such a system, probably also due to the larger crystallinity that is developed in a homopolymer system with respect to a copolymer one. So this brings me to the conclusion. We have investigated the possibility to have reversible actuation in photo-crosslinked polycaprolactone, specifically with certain composition of PCL-PEG copolymers and also on homopolymers. We find out a very satisfactory stress-driven effect, and the effect is mainly related to the evolution of the crystal phase, and the results show to be promising for artificial muscles. Whereas in the case of the stress-free two-way shape memory effect, we find out smaller elongation, which make think this system more related to smart hinges and grips. But at the same time, we saw that there are possibilities to further enhance or tune the effect by means of choices on the composition of the thermomechanical cycles, in particular on the separation temperature, or with strategies that are related to the homopolymer. And actually, we tried, just to show you briefly, on a PEG-based network. The results, and these were 3D printed by stereolithography. The results were, let's say, satisfying for what concerned the stress-driven effect, whereas we did not find the stress-free elongation. I would say that this is because the results are mainly overwhelmed by thermal expansion and contraction, but we are still investigating on the behavior of this system. And with this, I conclude. I'd like to thank you for your attention. Thank all my collaborators and Metal Press Donati and Rubinetteria Bresciani for the support given to our research. Thank you.